Class, in today's toolbox, we're going to be discussing the inverse of a matrix. The inverse of a matrix is very important because it is the key to conducting the equivalent of division with matrices. It is more difficult and involved to compute a matrix inverse than it is to simply do matrix addition, multiplication, or subtraction. However, it is an important tool for working with matrices. In my research, I almost always use computers to calculate a matrix inverse for me. However, it is very important for you to get an understanding of how matrix inverses work and where they come from, so that you'll have a solid foundation with them, since they will appear again in this course and are likely to pop up in your research as well. So that's what we're going to focus on in this toolbox, learning how to work with matrix inverses so that we can use them as a tool for studying population dynamics, endangered species, migration, and many other topics. If you remember back to the second toolbox in this course, we discussed matrix addition, subtraction, and multiplication. To add two matrices, you simply add the corresponding elements of each matrix to form a new matrix. To subtract two matrices, you simply subtract the corresponding elements of each matrix to form a new matrix. To multiply two matrices, you take the dot product of the appropriate row from matrix 1 and the appropriate column from matrix 2. Or in other words, the product of the two matrices is determined by summing the elements in one row of the first matrix multiplied by the elements in one column of the second matrix. So we talked about addition, subtraction, and multiplication. But if you were paying attention and you were curious, you may have noticed that we did not talk about matrix division at all. Matrix division is more complex. And before we learn how to do matrix division, I want to just remind you of some of the basics of division with normal scalar values. Division of two scalar numbers is completely equivalent to multiplication by the reciprocal. The reciprocal of any number is defined such that the reciprocal is multiplied by the original number yields the value 1. This basically means that the reciprocal of a number is simply 1 divided by that number. The reciprocal of x is written as either 1 over x or as x to the negative 1, since these two things are equivalent as we learned in the exponents section of the elementary functions toolbox. Given these definitions, we know that a over b equals a times b inverse. We also know that 5 over 6 equals 5 times 1 over 6. Okay, that's simple. We all understand that. Why am I wasting time talking about it? Well, I'm doing it because it's important to remember this definition of scalar division allows us to define an equivalent notation for matrix division. Alright, for scalars we've determined that division is the same thing as multiplication by the reciprocal, and that the reciprocal is defined such that a times the reciprocal of a equals 1. So what would be the equivalent equation for matrices? What should be in those question marks there? You might think that it should be 1, but if you stop and think about what that means, you'll realize that there's a problem with that. If you multiply, say, a 2 by 2 matrix by another 2 by 2 matrix, what do you get? You don't get a scalar value. You get another 2 by 2 matrix. Most of the time, multiplying one matrix by another gives you not a scalar, but another matrix. So if we wanted to define an equation such that a times a inverse equals 1, it simply would not work for most matrices. But what if instead of putting in the scalar 1 for the question marks, we put in the identity matrix? If you remember back to Toolbox 1.2, the identity matrix is a square matrix with 1s along the diagonals. The identity matrix also has the property that if you multiply it by an appropriate sized matrix, you get the same matrix back. Okay, so this has the potential to work. It is similar to saying that the scalar a times its reciprocal is equal to 1, because 1 is really the multiplicative identity for scalar values, while the identity matrix is the multiplicative identity for matrices. Hopefully you can start to see where we're going with this. If we can find that inverse matrix, then multiplication by the inverse matrix is how we will define matrix division. But how do we calculate that inverse matrix? Well, First, let's just make sure that we know how to check if one matrix is the inverse of another. Let's take one example. We'll take the matrix A and make it equal to 1, 1, 2, 3. And we'll make the matrix B equal to 3, -1, -2, 1. We're going to ask the question, is B the inverse of A? To figure this out, we need to multiply A times B and see if we get the identity matrix. Okay, the first element of X is equal to 1 times 3 plus 1 times -2. So that is equal to 1. The second element is equal to 1 times -1 plus 1 times 1, so that's equal to 0. We're good so far. The third element is 2 times 3 plus 3 times -2, so that gives us 0. And the fourth element is equal to 2 times -1 plus 3 times 1. So if we look at our final matrix of 1, 0, 0, 1, we can see that it does have 1s along the diagonals and 0s elsewhere. So this is the identity matrix, and we conclude that B is, in fact, the inverse of A. Let's try one more example. We'll make C equal to 2, 2, 2, 3, and D equal to 1, -1, 2, 3. And then we'll ask if D is the inverse of C. We'll start off again by calculating the first element as the dot product of the first row of C times the first column of D. However, this time we find that 2 times 1 plus 2 times 2 equals 6. If the first element of the matrix is 6 and not 1, then we know that it cannot be the identity matrix. We don't even have to finish multiplying this matrix out. Y is definitely not the identity matrix, so D is definitely not the inverse of C. Okay, so we figured out how to determine whether or not two matrices are inverses. Our next step is to come up with a way of finding the inverse. Our recipe for finding the inverse of a square matrix A will have the following steps. First, form a partition matrix that includes the matrix A as well as an identity matrix with the same dimensions as A. Next, use elementary row operations to rearrange this matrix into a new partition matrix that includes the matrices C and D, where C is either the identity matrix or it contains a row of zeros. If we are able to work it out so that C contains the identity matrix, then D is actually the inverse of A. On the other hand, if C contains a row of zeros, then we have determined that A does not actually have an inverse. In this case, we refer to it as a singular matrix. Alright, clearly the elementary row operations are very important to this process, so let's first get a reminder of our elementary row operations. Our elementary row operations allow us to make three different modifications to a matrix or a system of equations. We can swap two rows, we can multiply a row by a non-zero number, or we can add a multiple of one row to another row. Remember from Toolbox 1.3 that these elementary row operations do not fundamentally change a system of equations, so they really don't change the meaning of our partitioned matrix. Next, let's try this approach out in practice. Alright, let's try to find the matrix inverse for the matrix A equals 2, 3, 1, 5. First, we will create a partitioned matrix that includes A and the identity matrix. This partition matrix, of course, will have the A matrix 2, 3, 1, 5, and the identity matrix 1, 0, 0, 1. We now want to use our elementary row operations to rearrange this matrix so that we have the identity matrix on the left side of the matrix. First, we will subtract 0.5 times row 1 from row 2. This gives us 0 in our first element, 3.5 in the second element, negative 0.5 in the third element, and still 1 in the fourth element. Now we can just divide the entire second row by 3.5. This gives us 0, 1, negative 1/7, and 2/7. This means that we're about half the way to getting the identity matrix in that left side of the partition matrix. Our next move will be to subtract 3 times row 2 from row 1. This gives us a top row of 2, 0, 10/7, and negative 6/7. Now if we just divide row 1 by row 2, if we divide row 1 by the scalar value 2, we can get the identity matrix into the left-hand side of the partition matrix. Okay, so this tells us that our inverse matrix should be 5/7, -3/7, -1/7, and 2/7. Let's check and make sure that this actually works. To make sure that D actually is the inverse matrix for A, let's multiply them together. The first element will be 2 times 5/7 plus 3 times -1/7, so that is equal to 1. The second element will be 2 times -3/7 plus 3 times 2/7, so that is equal to 0. The third element is 1 times 5/7 plus 5 times -1/7, so that is equal to 0. And the final element is 1 times -3/7 plus 5 times 2/7, so that is equal to 1. So you can see that we've gotten the inverse matrix back. So that actually works. So now we actually know how to find the inverse of a matrix. Since we know how to find the inverse of a matrix, and we know that multiplying by the inverse matrix is the equivalent of dividing by a matrix, that means we've figured out how to do matrix division. Let's try an example then. Let's remember back to Toolbox 2.3, our toolbox about functions of matrices, and specifically our example about grasslands. We were thinking about restoring a grassland. The grass that we are trying to restore has 3 different life stages: seedlings, vegetative adults, and generative adults. The seedlings have a 0.6% chance of surviving for a year to become vegetative adults. The vegetative adults don't reproduce and have a 40% chance of transitioning into generative adults after a year and a 40% chance of remaining vegetative adults by the end of the year. The generative adults also have a 40% chance of remaining generative adults and a 40% chance of transitioning back into vegetative adults. The generative adults, however, also produce 500 seedlings each year. Based on this information, we constructed a matrix P that keeps track of how many seedlings, vegetative adults, and generative adults we have in the population. We also generated a matrix G that encodes the probabilities that an individual this year will become some form of an adult next year and/or produce new seedlings next year. Multiplying P times G allowed us to quantify the population structure for next year. But what if we knew the population structure this year and we wanted to estimate what the population structure was last year? If the population structure for last year times G equals the population structure for next year, then the population structure for this year times G inverse should be equal to the population structure for last year. Let's just take a moment and remind ourselves why the inverse of G can help us figure out the previous year's population structure from this year's population structure. We know that, for instance, the population structure for the year 2021 can be estimated from the population structure for the year 2020 by multiplying G times P 2020. This was what we figured out in Toolbox 2.3. If both sides of that equation are equivalent, they have to give the exact same matrices, and it must also be true that we can multiply G inverse by both sides and have it still be true. So we can write that G inverse times the left side of the equation equals G inverse times the right side of the equation. Or in other words, G inverse times P 2021 equals G inverse times the product of G times P 2020. However, the associative property of matrix multiplication tells us that G inverse times the product of G times P 2020 is equal to the product of G inverse times G multiplied by P 2020. In other words, the associative property tells us that we can move the parentheses. But now that we've moved the parentheses, we can also rewrite the equation because we know that by definition, G inverse times G equals the identity matrix. So really, we have the identity matrix times P 2020 on the right-hand side of the equation. And of course, the identity matrix times the matrix P 2020 is simply the matrix P 2020. So we can see that if we can find G inverse, we will be able to calculate the previous year's population structure from this year's population structure. So let's try to find G inverse. First, let's remember our recipe. We need to start by creating a partition matrix with a matrix that we want to find the inverse of on the left side and the identity matrix on the right side. So that is G and the identity matrix. And of course, we can fill this partitioned matrix out with the actual values for G and the identity matrix. Next, we want to use our elementary row operations to rearrange this matrix so that we have an identity matrix on the left-hand side of the partitioned matrix. Let's remember again what the elementary row operations are. They are swap two rows, multiply a row by a non-zero number, or add a multiple of one row to another row. Okay, so let's get to work. When it comes to using the elementary row operations to get the identity matrix on the left-hand side of this partition matrix, we're really just following the same procedure that we did when trying to solve a linear system of equations. So let's think of it like that and define our first pivot. We want our first pivot to be in the top row. But there is a 0 in that position and a non-zero number below it, so we want to swap the rows to get the non-zero entry into the top row. So let's swap rows 1 and 2. This gives us 0.006, 0.4, 0.4, 0, 1, 0 in the top row. Now, since our pivot contains a non-zero entry, but that non-zero entry is not equal to 1, we need to divide the entire row by that non-zero entry. So that gives us 1, 66.67, 66.67, 0, 166.67, and 0 in the top row. Our pivot is 1, and if we look at all the entries beneath it, they are all 1, so we are happy and we can move on to our next pivot by moving down 1 and over 1. This puts our new suspected pivot in row 2, element 2. If we look at it, we can see that we have a 0 in this entry, but we do have a non-zero entry below it. So again, we're going to want to swap rows. This time we will swap rows 2 and 3, which gives us 0, 0.4, 0.4, 0, 0, 1 in the second row. Again, we'll divide by the non-zero entry in our pivot, which means dividing the entirety of row 2 by 0.4 to give us 0, 1, 1, 0, 0, 2.5 in the second row. We've now got a 1 in the pivot value, and when we check below it, we've got all zeros below it, so we can move on to our next pivot, which is down and to the right. This time we do have a non-zero value in the pivot, so all we need to do is divide by that non-zero value to finish off this row. So we'll divide 3 by 500, and we get 0, 0, 1, 0.002, 0, 0 in the third row. Next, we need to eliminate all the entries above this pivot. Our first step will be to subtract row 3 from row 2. This gives us 0, 1, 0, negative 0.002, 0, 2.5 in row 2. And we can move up to row 1. This time we have to subtract off 66.67 times row 3 from row 1, which gives us 1, 66.67, 0, negative 0.133, 166.67, 0 in the first row. Okay, now everything above our pivot is 0, so we can move along to our next pivot and eliminate all the non-zero values above it. This will require subtracting off 66.67 times row 2 from row 1, which yields 1, 0, 0, 0, 166.67, negative 166.67 in the first row. We've eliminated all the non-zero values above the pivot, and we're done. We've now got the identity matrix on the left-hand side of the partition matrix and G inverse on the right-hand side of the partition matrix. So in theory, all that we need to do is multiply G inverse times our population vector to find what the population structure was in the previous year. Let's go ahead and see if that actually works. We'll take the population structure that we previously computed in Toolbox 2.3 for the year 2022. In the year 2022, which was 2 years after our initial planting in our simulation without herbivores, we computed that there would be 30 vegetative adults, 30 generative adults, and 0 seedlings. Let's see what happens when we multiply by the inverse to compute the population structure for the year 2021. Of course, we've got to fill in the actual values for G inverse and P 2022. We then calculate our first element as the dot product of the first row and the only column, and this is 0 plus 166.67 times 30 plus negative 166.67 times 30. So of course it is equal to 0. The second element is the dot product of the second row times the only column, so that is negative 0.002 times 0 plus 0 times 30 plus 2.5 times 30, so it is equal to 75. And the final element is the dot product of the third row and the only column, so it is 0.002 times 0 plus 0 times 30 plus 0 times 30, so it is also equal to 0. If you remember back to Toolbox 2.3, this actually checks out. We had previously determined that P 2021 was 0, 75, 0, meaning there were 75 vegetative plants and no generative adults or seedlings. Let's just do it one more time to compute the population structure in the year 2020. P 2020 equals G inverse times P 2021. And again, we compute the dot products of the first row and the only column to find the first element, which turns out to be equal to 166.67 times 75, because the other entries in our population vector are both 0. And 166.67 times 75 is 12,500. Our second element is equal to negative 0.002 times 0 plus 0 times 75 plus 2.5 times 0, so that is equal to 0. And our last element is 0.002 times 0 plus 0 times 75 plus 0 times 0, so that is equal to 0 as well. So this tells us that our population structure for the year 2020 was 12,500 seedlings and no adults. That checks out with what we initially planned in Toolbox 2.3. So it seems that our matrix inverse approach really does work for allowing us to figure out the previous year's population structure from this year's population structure. That's it for this toolbox. Remember that the matrix inverse is a powerful tool to use for understanding population dynamics and many other properties. We will rely on it in future toolboxes as we investigate many different properties of the Earth system. For now, don't forget to take the mini quiz on Canvas.